You cannot stop in space, not because the laws of physics prevent it, because the concept of stopping doesn't exist where we think it does. When astronauts talk about being stationary in orbit, they're moving at 17,500 miles per hour. And that velocity is the only reason they appear still. The moment you actually stop, the moment you remove every vector of motion from your body relative to every other object, you're not at rest. You're at a different kind of motion, one that isn't visible to the instruments measuring the ones that are. And the question is whether that distinction matters when the distinction itself is the foundation of how we understand momentum altogether. I ran into this while working on something completely unrelated, a problem about reference frames in orbital mechanics that had nothing to do with any of this. I was reading through old NASA documentation, the kind that doesn't end up in popular accounts, and I came across a single sentence in a technical manual from the 70s. An engineer had written, almost as an afterthought, "There is no such thing as a stationary spacecraft." I spent 3 hours trying to understand what that meant. I thought it was a poetic way of saying something about constant acceleration or gravitational wells. It wasn't. It was literal. And the more I looked into why that sentence was true, the more I realized that what we call stopping in space is actually a choice about what you're measuring yourself against. And that choice is so deeply embedded in how we think about motion that we don't notice we're making it at all. I'm still not entirely certain I understand the implications, but I've gotten closer, I think. Close enough to see why this problem has been sitting at the edge of physics for longer than most people realize. Here's what I want to walk you through. First, what most people believe about motion and stopping, and I want to be clear that what most people believe is not wrong. It's incomplete in a very specific direction. What the research actually shows is something that contains what most people believe the way a larger shape contains a smaller one. The smaller thing is still there, still true, but it's not the whole picture. The part that's missing from most discussions is not missing because anyone is hiding it. It's missing because it requires accepting an answer that doesn't feel like an answer. That answer is called the principle of relativity, and it's been understood for almost 400 years. The problem is not that we don't know it. The problem is that we don't live it. We talk about it in physics classes, and then we go back to believing that there are some things that are actually still and some things that are actually moving, and that distinction is real in a way that our reference frame shouldn't matter. That's where this gets strange. Let me start with what you already know, the version of motion that lives in your body every day. You're sitting still right now. The chair isn't moving. The room isn't moving. That sense of stillness is real. You can feel it. But here's the thing that physics discovered and then never really convinced anyone of. That stillness is not a property of the chair. It's a relationship. You're still relative to the chair. The chair is still relative to the floor. The floor is still relative to the earth. And the earth is still relative to what? That's where most people stop thinking. They assume the answer is obvious. It isn't. The earth is rotating. one rotation every 24 hours. If you're sitting at the equator, you're moving at about 1,040 miles per hour relative to the Earth's axis. If you're in New York, you're moving at about 800 miles per hour. If you're at the poles, you're barely moving at all. But none of that matters because you're all rotating together. You don't feel it. And the reason you don't feel it is the reason this entire problem exists. Now add another layer. The Earth is orbiting the Sun, 67,000 miles per hour. Relative to the Sun, you're not still. You're moving at a speed that would incinerate most spacecraft. The entire atmosphere of Earth is moving at that speed. The mountains are moving at that speed. You are moving at that speed, and you don't feel it. And the reason you don't feel it is because the chair is also moving at that speed in exactly the same direction. Everything around you is accelerating toward the Sun together. Your body has no way to detect that motion because there's nothing standing still relative to you to measure against. Add another layer. The Sun is moving through the galaxy at roughly 480,000 miles per hour. The galaxy is moving through the universe. The universe itself might be moving through something we don't have a name for. And at every single level, you're moving with it, and at every single level, you don't feel it. And at every single level, the reason you don't feel it is the same. You're not accelerating, you're moving at constant velocity relative to whatever structure you're embedded in. This is where a physicist would pause and say something like, so what? And that's exactly the right question. So what? If you can't feel the difference between stillness and constant velocity, does it matter that we're technically always moving? For life on Earth, no. It doesn't matter at all. The distinction is purely conceptual. And yet, that conceptual distinction is the entire foundation of how we understand what happens when you try to stop in space. Imagine an astronaut in a spacecraft. The spacecraft is in orbit around Earth at 17,500 miles per hour. That's not a metaphorical speed. That's what it has to be moving to maintain orbit. The astronaut is moving at that speed. They feel still because the spacecraft is also moving at that speed in the same direction. They're not accelerating relative to the chair they're sitting in. There's no force acting on them except the gravitational pull of the Earth, which is exactly balanced by the curvature of their orbital path. It's called free fall, and it's the only thing in physics that actually feels like rest. Now the astronaut decides to stop. They want to come to a complete stop. What does that mean? It means they want zero velocity relative to something. But relative to what? Relative to Earth. There's a problem. If they reduce their velocity to zero relative to Earth's center, they fall. Gravity pulls them down. They can't stay in orbit and have zero velocity relative to Earth at the same time. One of those things has to give. If they reduce their velocity to zero relative to Earth's surface at their current altitude, they fall even faster because they'd be moving slower than orbital velocity. So they have to either fall back to Earth or move forward to a higher orbit. They can't actually stop. But wait, maybe they meant zero velocity relative to the Sun. That's a different problem entirely. The Earth is moving at 67,000 miles per hour relative to the sun. If the spacecraft wants to have zero velocity relative to the sun, it has to slow down from not just its orbital velocity around Earth, but also cancel out the entire velocity of Earth's orbit. That would require an enormous amount of fuel. Practically speaking, it's impossible. And even if they managed it, they'd still be moving relative to the galaxy. Still moving relative to the cosmic microwave background radiation, which is the closest thing we have to an absolute reference frame in the universe. And there's no guarantee that's actually still either. This is the rupture. This is where what we call stopping breaks. There is no place in the universe where you can actually achieve zero velocity, because there is no place in the universe that is actually still. Stillness isn't a destination, it's a choice about what you're measuring yourself against. And the moment you're in space and you try to make that choice, you realize it's not your choice to make. The choice was made for you centuries ago, embedded in how we built our instruments and how we trained our eyes to see motion. The physicist Albert Einstein understood this completely, and he spent years trying to convince other physicists that this problem was fundamental. He called it the principle of relativity, and what it says is this: there is no preferred reference frame. There is no place in the universe that is more actually still than any other place. Motion and stillness are always relative. They're always a relationship between the observer and the observed. And if you accept that, you have to accept something else. You have to accept that when an astronaut in space comes to a stop, they're not stopping in any absolute sense. They're just changing which reference frame they're measuring themselves against. They're deciding that relative to Earth, relative to this particular axis, relative to this particular definition of what stillness means, they are now still. And that decision is perfectly fine. It works. It's useful. It's just not true in the way most people think true means. I need to correct something I just said. I called Einstein's principle of relativity something he invented, but he didn't invent it. Galileo understood it 300 years before Einstein was born. Galileo realized that there's no way to detect motion if you're moving at constant velocity. He wrote about it in terms of a ship sailing smoothly across the sea. If you're below deck and the ship is moving at constant velocity, you can't tell. Drop a ball, it falls straight down. The ship's motion doesn't matter. The ball moves with the ship. Everything moves with the ship. Constant velocity is indistinguishable from stillness as long as you're inside the system. The reason I corrected that is because it matters for the next part. Einstein didn't invent relativity. He extended it. He took Galileo's observation and showed that it applied not just to velocity, but to acceleration, and not just to space, but to time itself. But the core insight is older, and that means this problem, the problem of what it means to stop, is older too. We've been grappling with it for centuries. We just don't realize we're grappling with it because we've built a language around the assumption that there are some things that are truly still. Here's where it gets complicated. You're probably expecting this to start wrapping up. I thought so too when I first encountered this, but the part I haven't addressed yet is the part that makes the question actually hard. The part that has resisted simple answers for a surprisingly long time. When a spacecraft in orbit fires its thrusters and reduces its velocity relative to Earth, something happens that is easy to describe but difficult to think about clearly. The astronauts on board feel it. They feel themselves accelerate. They press back into their seats. There's a force, but that force isn't coming from anywhere external. It's not coming from a push against the vacuum. It's coming from the spacecraft's own engines. The astronauts' bodies want to keep moving in a straight line. The spacecraft decelerates. The astronauts' bodies don't. So there's a force between the astronauts and the seats. The astronauts feel that force. They feel like they're slowing down. But here's the problem. To an observer floating in space, far away from Earth, far away from any planet, any star, any gravitational well, the astronauts aren't slowing down at all. They're accelerating. They were moving at 17,500 miles per hour in one direction. Now they're moving at 17,400 miles per hour in that same direction. From their perspective, they're moving slower. From the distant observer's perspective, the astronauts have accelerated in the opposite direction. They've added velocity opposite to their original vector of motion. The two descriptions are completely incompatible, and they're both correct. Actually, let me be more precise about that. The distant observer would see the astronauts fire their thrusters and then change trajectory slightly. The astronauts would see themselves slow down and fall into a lower orbit. Both descriptions are true. Both observers are using legitimate reference frames. But the physical sensation the astronauts feel, the acceleration pushing them back into their seats, that's real. That's not a matter of perspective. That's a force. That's something actually happening. And this is the hard question. If motion is purely relative, if there's no such thing as absolute motion or absolute rest, then what is acceleration? Acceleration is when you feel a force. But a force is something real. A force changes the state of an object's motion. A force causes acceleration. And acceleration, unlike constant velocity, is not relative. You can feel acceleration. You cannot feel constant velocity. An astronaut moving at 17,500 miles per hour feels nothing. An astronaut accelerating at 0.001 miles per hour per second feels something. That difference is real. That difference is not relative. So we have a paradox. Motion is relative. Acceleration is absolute. Relativity is relative. Acceleration is not. The question of what happens when you try to stop in space is actually the question of what happens when you try to change your velocity. And changing velocity means accelerating, and acceleration is the one thing in the universe that is not relative. It's the one thing you can measure without reference to anything else. You can feel it in your body. You can measure it with instruments that don't require you to know where anything else is. Acceleration is the thing that breaks the perfect symmetry of relativity. Einstein spent years thinking about this. He realized that acceleration and gravity are connected in a way that most people don't understand. When you feel pushed back into your seat during acceleration, you feel the same sensation that you feel when sitting in a chair on Earth. Gravity is pushing you down. A spacecraft accelerating is doing the same thing. It's pushing you back into the seat. The two sensations are indistinguishable. And Einstein realized that this wasn't a coincidence. Gravity and acceleration are the same phenomenon seen from different reference frames. A spacecraft accelerating is equivalent to sitting in a gravitational field. The math works out, the experience is identical. But this creates a new problem. If acceleration and gravity are the same thing, then what is gravity really doing? What is the mechanism? Einstein answered that question with general relativity. He said that massive objects curve space and time around them. Gravity isn't a force pulling you down. It's the geometry of space itself. You're moving in a straight line through curved space. The curvature of space is what changes your trajectory. But the sensation is the same as if you were being pulled. The reason this matters for the question of stopping in space is that it reveals something about what motion really is. When you're in a spacecraft trying to stop by decelerating, you're not actually doing anything to the motion itself. Motion is just what happens when you're at point A and then at point B. What you're doing is changing your reference frame. You're changing what you measure yourself against. But the acceleration you feel is real. The force pushing you back into your seat is real. And that force is indistinguishable from gravity, which means that trying to stop accelerating in the opposite direction of your motion is actually like falling sideways. It's like jumping up off the ground on Earth. The Earth curves beneath you. Space curves beneath the spacecraft. The effect is the same. You might be thinking that this only applies in specific conditions. And if so, you're right to think that far away from any gravitational source, in the middle of intergalactic space, a spacecraft could accelerate and there wouldn't be any curvature of space to explain it. But that doesn't rescue the original intuition in the way you might hope. Because Einstein's insight wasn't just about gravity. It was about something deeper. It was about the fact that acceleration and the sensation of being stationary in a gravitational field are mathematically identical. And if they're identical, then what's the difference between them? Maybe there isn't one. Maybe acceleration is always relative to something. Maybe when you accelerate in a spacecraft, you're not accelerating relative to the fabric of space itself. You're accelerating relative to something else, something we don't fully understand yet. The current thinking, and this is where I need to be honest about the limits of what we know, is roughly this. When you accelerate, you are genuinely accelerating. You can measure it, you can feel it, and you're accelerating relative to something called an inertial reference frame. An inertial reference frame is something moving at constant velocity. It could be Earth, it could be a distant galaxy, it could be the cosmic microwave background radiation, it could be something else entirely that we haven't discovered. The point is that there's something. There's always something. There's no such thing as accelerating relative to nothing. This is where the question of stopping in space stops being about mechanics and becomes about the nature of space itself. If you can't accelerate relative to nothing, then what are you accelerating relative to? And if there is something, a reference frame that defines inertia, then is that something special? Is it more fundamental than anything else? Or is it just another choice, another layer in an infinite hierarchy of reference frames? Each one defining stillness and motion for the things inside it. I think that's probably the honest place to stop here for now. Because the question you're asking, what happens if you try to stop in space, is not actually a question about physics. It's a question about what the word stop means. And the answer depends entirely on what you decide to measure yourself against. If you want to stop relative to Earth, you fire your thrusters in the direction opposite to your orbital motion. Your velocity relative to Earth's center decreases. You feel yourself pushed back into your seat as you accelerate in that direction. You fall. Your trajectory changes. You orbit lower. Eventually you fall all the way down and burn up in the atmosphere. You don't stop. You change direction. If you want to stop relative to the sun, you need to do something much more extreme. You need to cancel out the entire velocity of Earth's orbit. 67,000 miles per hour plus your orbital velocity around Earth. It would take more fuel than you have. You can't do it practically. But theoretically, if you could, you'd achieve zero velocity relative to the sun. And then you'd be falling directly toward it. The sun's gravity would pull you in. You wouldn't stop. You'd just be falling toward a different destination. If you want to stop relative to the center of the Milky Way, you'd need to cancel out the velocity of the entire solar system through the galaxy. 480,000 miles per hour. Good luck. And if you managed it, you'd still be moving relative to the cosmic microwave background. You'd still be moving relative to the Andromeda galaxy. You'd still be moving relative to something. There is no place in the universe where you can actually achieve zero velocity in all reference frames simultaneously. It's not possible. And the reason it's not possible is not because you don't have enough fuel or because the numbers are too big. It's not possible because the concept of absolute stillness doesn't exist. There is no absolute reference frame. There is no place that is more truly still than any other place. Everything is moving relative to something. And the moment you're in space trying to decide what you're still relative to, you realize that the decision isn't technical, it's philosophical. It's a choice about what you care about measuring yourself against. That number I mentioned at the beginning, 17,500 miles per hour, the speed of Earth orbit. I understand it better now in the ways that can be made precise, in terms of orbital mechanics, in terms of the balance between velocity and gravity, in terms of what happens when you change that balance. But I understand it less in the ways that cannot be made precise. In terms of what that velocity means when there's no place in the universe that is actually still to measure it against. What does 17,500 miles per hour mean? Miles per hour relative to what? The answer is always relative to something else that's also moving. And that answer never stops echoing. The question gets cleaner the deeper you go into it. The discomfort gets worse. You cannot stop in space because there is nowhere to stop to.